Hello, comrades. This is part 2B of my comp methods homework 2. And in this section, I'm going to explain and implement Newton's method for finding the root of a vector or an n-dimensional function. So, what's the difference between what I just did in the last part and what I'm going to do in this part? Well, I'm still going to be doing Newton's method both times, but this time I'm going to be using Newton's method for basically like a systems of equations, or finding the root of systems of equations, or maybe you even talk about finding like the root of a multi-dimensional function. So a multi-dimensional function, this really echoes back to when I created a function of the Jacobian in my first homework for comp methods. So maybe you could go back there to learn a little bit more about a Jacobian matrix. But essentially you have f. F is a function with k variables and k functions. So what does that mean? Well, f is a matrices of a bunch of functions, and each function is defined in terms of a certain number of variables. But for f, for this method I'm going to be using, it's the same number of variables as there are functions. So it's going to be this the Jacobian is going to be like a big square array. Because remember, the Jacobian solves f1, f2, f3, and then it solves in terms of like x1, x2, and x3. And I'm just going over this briefly. Go check out my video on the Jacobian matrix if you haven't seen it already. But anyway, this is all fine and dandy, but what is the Jacobian? The Jacobian is essentially a derivative of a matrices of functions with a bunch of different values. So that's all the Jacobian is. And, you know, if you remember last video, I used Newton's method like this. I said that my next guess is going to be my first guess minus the function evaluated at the first guess divided by the function, or the derivative of the function evaluated at the first guess. And what that allows you to do is sort of jump through here and make a bunch of guesses, find the derivative, use that to do some regression, and eventually you will find the root. So let me go down here to where I started the video at, if I can find it. It's down this way, and yeah. So if we try to do this for multiple functions within a matrix F, then we need to say that our new guess, so xn plus 1, is just our old guess minus the Jacobian of f evaluated at our old guess, but it's actually the inverse of that value, with a matrix multiplied by the function f evaluated at my initial guess. So that's just sort of rewriting what we did in the last video, but now it is in terms of a function with multiple variables. So with all that said and done, let's go ahead and go to the homework. And you can see here's my Newton's method function up here. I'm going to try to point out the parallels between what I did up there and what I'm going to do down here. But anyway, sweet. So I will define capital Newton. We'll say it's capital because it has multiple functions. And that will take all the same inputs as my old Newton's function, right? With one maybe small change I'll make for clarity. This capital Newton is going to take a capital F, and I'm just calling it a capital F to signify that this function is actually a matrix of a bunch of little functions. That's what this function we're passing in and trying to evaluate with capital N Newton is going to be. So then, similar to Newton's method, we are going to return our final guess, which should be the roots of the equation, right? And we have an initial guess. We have this function. I'll probably start out by evaluating the, well, I guess how we started out here. We started out with the first Newton's function by evaluating the gradient or the derivative of whatever function I passed in there. So let me go ahead and say that maybe f jax, so the Jacobian of f, is just going to be jax, if I can spell, jax.jacobin. So jax.Jacobian of some values. So it needs to be the Jax Jacobian of whatever that function is I passed in there. And then once I've done that, I need to go forward and what else do I need to do? Well, I should probably evaluate f at point 0, which is just going to be f evaluated at the initial guess. So this is my value of f at my initial guess. And so now I'm going to go in here and I'm going to maybe say, well, no, I don't want to return. Once I've done that, I want to start the loop, right, for I in the range from max iter. I want to iterate through here, and what I want to do. Well, I will say that x1, so my next guess, is going to be my first guess, right? And now it gets a little bit more complicated. So my next guess, xn plus 1, is going to be my first guess, minus the Jacobian of f, evaluated at xn, and it's going to actually be the inverse of that. So how do we do this in Python? Well, I can't go through and I can say I want to take the JNP lin algebra, so from Jack's NumPy's lin, L-I-N-A-L-G. Yeah, okay, there it is. From Jack's NumPy's lin algebra library, I think this is a library, I want to go ahead and access the, what's it called? I am totally blanking on this all of a sudden. That's kind of funny. I am going to access the, it's not the norm. I will be using the norm later. It is the inverse. Yes, the inverse. And I want to take the inverse of f, the Jacobian of f. But then I also want to evaluate the Jacobian of f at my guess, or whatever my guess is at the time. So that's pretty sweet. Now I need to do a matrix multiplication, which in Python is an @ sign. And I need to matrix multiply that with f evaluated at xn. So I can just say f, or I guess that's just f0. I already evaluated that up at the top. So now that I've done this, I can go ahead and start trying to check and see how close is this guess to being an actual root of the function f. And so I can go ahead and I can say that f1 is just going to be f evaluated at x1. Pretty sweet. And then I'm going to check. So I'm going to say if f1 is less than tolerance, then I want to break out of the loop because I'm done. f1 is a really low value, which means it's basically a root because f1 is basically 0 at that point. And this isn't correct, but let me come back to it later and finish up the rest of the formula, or the rest of the function. So after this, I need to just do what I did before, and I need to say that x0 is what used to be my, so I'm moving on to the next guess. So what I just calculated here is my new base guess, and then of course I need to go ahead and redefine my initial value of f as just f1. I'll go ahead and put a space in there just to be nice. And if I run this, I won't get any errors, but this isn't actually correct, and I'll get an error, and I'll use that to spring back to this function and figure something out. So anyway, I have this Newton function. It doesn't work, but we'll pretend like it works, and then I'll explain why it doesn't work. But I need a function to evaluate. Well, fortunately, SciPy optimized root has a built-in function that, or it doesn't have a built-in function. It has just this example function. This is something my professor used in class, so I'm going to go ahead and copy it just to be simple, save some time in the video explaining something that doesn't really even super matter. Now I need to return not just a list of these two values, but I actually need to return a Jack's NumPy array of those values. So I'll go ahead and make a quick modification and say I want to return a JNP array. And so I have that. Now I think I'm ready to just go capital Newton, evaluate f is just going to be the function I stole from SciPy optimized root, and then I need some initial conditions. Well, what should the initial conditions be? I'll go ahead and call those x0, but let's just say my initial conditions are going to be an array of values, because you look at this function, it's f in terms of x, but there are two functions. One is what I'm highlighting here, the second function is what I'm highlighting here, but then there's also two independent variables. There's this x0 and there's also this x1. So I need to say that my initial guesses, or the x0, so that's a little bit confusing terminology, but my initial guesses are just going to be a Jack's NumPy array of two values, let's just say 0 and 0. And I'm just making up those two values. They're not correct, but they're close enough to where we'll get a valid result. So now I should be good to maybe delete these things. I like it more when it's not there. And I will get an error. And I think this is the error I was expecting to get. It says Jack REV requires real or complex valued inputs, but got an integer. If you want to use Boolean or integer valued inputs, use VGP. This stuff isn't actually the solution to the problem. So it's not exactly clear here, but this is going back to my Newton's function, and it's having an issue with this line of code right here. Because what I'm doing is I'm saying if the function evaluated at my guess is less than the tolerance, so if it's really close to 0, because tolerance is a really low number, then it wants to break out of the code because we're done, we're good to go. But that is not actually what I need to be doing here. And if you look at it, it becomes clear when you think about what f1 is. This f1 right here is an array of values. And it's like it's an array of values of the form. It has two values, right? Because it's the solution to the function evaluated at these independent variables. So it's going to have one value dictated by this function, and then another value dictated by this function right here. So what I actually need to do is find some way to combine all that, and the way I'm going to do that is by taking another function from Jack's NumPy, and I'm going to go linear algebra norm of f1, right, of the function 1. So I'm taking the Jack's NumPy's linear algebra norm of f1. Or not the norm, but the magnitude is what I would call it. And once again, the magnitude of a vector or the magnitude of an array or matrices or whatever is just it's all the values in the matrices squared and then added up, and then the square root of them is taken. So it's kind of like an average almost of all the values, but it's always positive, so I don't have to take the absolute value of it. But I can just make sure that is less than tolerance, and then I can break out of the loop. So I'll go ahead and run this, run function again just for the heck of it, and let's see what this initial condition gives me. And it is still pissed with me because I made a minor error. I forgot that I need to set this array as two integers of 0, not just the value 0, but I need to put a decimal point after it to indicate that it is a float, not an integer. Because if it doesn't have a decimal point, then it thinks it's an integer. So now if I run it, I should get an array of two values. These are the roots of the function I specified up here. So that's pretty sweet. That's pretty great. And that is actually an explanation and implementation of Newton's method for finding the root of a vector function. So a function with multi-dimensions is what I called it in here. With that, I finished up part 2b. I hope you enjoyed the video, and I hope you learned a little bit. And above all else, I hope you just have a wonderful day. So, bye-bye.